Alright, y'all, so we did cross products, went over cross products last time. We're going to start to apply those cross products with torques, and then we'll also use them again next semester when we do magnetic forces that come up both times. So torques are, well, first of all, what is a torque? Like when you hear of a torque, what do you think about? Huh? Okay, yeah, so a torque will cause rotation. In fact, a torque will act a lot like a force. And in fact, we can even think of a torque as like an angular force. That is a force that causes rotational motion. So when you think of torque, I always think about what? A what? Okay, yeah, a drive shaft, because it provides a certain torque, right? What's that, Michael?
A car.
Okay. I always think of a torque wrench. You don't think of a torque wrench? Yeah, maybe not. Yeah, a torque wrench provides a certain torque on a nut or on a bolt. Do y'all know what the units on a torque wrench are?
Inch pounds or foot pounds?
Foot pounds, or more particularly Newton meters. Right? And if you're in the SI system, some torque wrenches have Newton meters on them, or foot pounds. And that's a measure of a force, pound or Newton, times a distance, which is the foot or the meter. And that distance is the length of the torque wrench, basically. So the torque that you get off of a torque wrench is equal to the force that you apply to the end of the wrench times the length of the wrench. Right. So a torque is just a force that's applied at a certain distance from the axis of rotation, or we call that the moment arm. So let's see, Newton's second law, remember F equals ma, also extends to rotational motion. And so just like forces cause acceleration, right, F equals ma, that's Newton's second law, torques will cause an angular acceleration. This was, if you recall, we called this alpha. And so you can think of a torque as an angular force. It's a force that causes an angular motion. Angular. I say this because all along we've been having these analogs between linear and rotational motion. Remember we had x, where now we're thinking in terms of theta. Before we had v, and now we're thinking in terms of omega. Before we had a, and now we're thinking in terms of alpha. All these rotational quantities, radians per second squared. And now, before, whereas we had force, now we're going to think in terms of torques. So if we translated those linear quantities into angular quantities, then we'll do the same here with torques. Whereas before we were talking about forces, now we're talking about torques. We can calculate the torque in a couple different ways. So this is like a torque wrench. We have a force that is applied here. This is the moment arm, which is the distance from where the force is applied to the axis of rotation. This is the distance from where the force is applied to the axis of rotation. Sometimes we'll deal with problems where that moment arm is defined as just a distance. Sometimes we'll deal with problems where it's actually defined as a vector. So we'll see both of those. The torque is equal to the cross product of R and F. Go down from here. So it's equal to R cross with the force, so the cross product of the moment arm vector and the force vector. And so if you recall, for cross products A cross B, the magnitude is equal to the magnitude of B times magnitude of A times the magnitude of B times the sine of the angle between them. That's a basic property of cross products. That's going to be the same for torques. So the magnitude of the torque is going to be RF sine of theta. And we'll use both of these terms. Sometimes I'll give you R and F in terms of in vector quantities with IJK notation, and then it's easiest to use the cross product to find the net torque. And sometimes I'll just give you the magnitudes of the force and the moment arm with the angle between them. So on that previous slide here where I had this figure, if I wanted to know the torque here, let's say that this force was 2 newtons and the length of this wrench was, you know, 0.2 meters, and let's say that this angle is 30 degrees, then the torque, the magnitude of the torque would be RF sine theta, where I have R is 0.2, F is 2 newtons times the sine of 30. So you remember, what was the purpose of the sine theta term in the cross products? The cross product, the purpose of the cross product was to take two vectors and multiply them, but we were looking for particular components of those vectors. So what is the purpose then of the sine theta term in this? Find the y, you're right. The y component, right? Or more particularly, not necessarily the y component, but the perpendicular component. Because when you're moving in a circle, right, where is the y-axis? It changes, right? But we're looking then, this f sine theta term gives us, as Zach said, the y component, or more importantly, the perpendicular component. So if I were to draw f sine theta on this, it would look like this. So this is the f sine theta, and then we multiply this times this, and that gives us the torque. Now, if theta is equal to 90, what is the torque simplified to? What is the sine of 90? It's just 1, right? So the sine of 90 is 1, and so if my theta goes to 90, then my torque is just R times F. So if our angle between F and R is 90 degrees, since the sine of 90 equals 1, then the torque just becomes R times F. All right. So you get the maximum torque whenever you apply a force at an angle that's perpendicular to the moment arm. So if you imagine the door here, my moment arm is the distance from here to here, just the width of the door. You'll see? Not really. Oh, there you are. Yeah, so this is the length of my moment arm, the distance from the axis of rotation, which is the hinge, down to the edge of the door. If I want to open the door, I want to first apply a force at 90 degrees to provide the maximum torque at 90 degrees. Because if I apply a force at some other angle than 90 degrees, then I'm going to provide less torque. The reason for that is that if I provide a force at an angle, not at 90 degrees, then one component of that force is providing the torque, and one component is providing no torque at all. Right? The component that's parallel with the moment arm. Right? The extreme of that is if my angle is 0 degrees. What would that look like if my angle is 0 degrees? Yeah, like I would have to, I'd have to be pushing like this. And nobody's ever going to open a door like this, right? Y'all try it and see what happens. You basically look like an idiot, right? You're trying to, damn door won't open, right? So if I have an angle of 0 degrees, then the sine of 0 is 0, and then you have no torque at all. All right. The sign for torque, we've already said, is Newton meters. You also find it in foot-pounds, but it's just a distance times a force. Distance times a force. Of course, we'll use Newton meters. This is the same unit as something else that we dealt with. What is that? Do y'all remember? A force times a distance. What was that? Oh, I can't remember. Huh? Yeah, it's the same as joules, right? Or it was the unit for work. Remember, work was force times displacement, which is the same as energy. And so, but it's not the same. So torque and work or energy are not the same. All right. This is a force that provides a rotation, and not a force that provides a linear translation, like an acceleration. Okay. Now, just like we had before, clockwise torques are going to be negative, and counterclockwise torques are positive. All right. So if I have torques that are in the clockwise direction, I count those as negative. And if I have them in a counterclockwise direction, I count those as positive. Those aren't directions. Those are going to be signs that will allow us to add up torques appropriately. Let's do this quick test. In this, I want you to add up all the torques that are acting on this. And click in with the appropriate answer. So. Just a second, I'll give you a little preview on that. So here I have this bar. It's rotating about a point C, and there are 3 forces acting upon it. I want to know what is the net torque that is acting on this bar. What you want to do in this case is first identify the forces that are causing torques. Now this bar is rotating about this axis right here, point C. And so there are 3 forces, but how many forces are actually causing torques? There are only 2 that are causing torques, because one of the forces is at a moment arm of 0, and so it has 0 torque. Likewise, if I had a force that was just pushing in this direction, that also would not cause a torque. It would not cause any rotation. But in this case, one of those forces does not provide any torque at all. And then you want to ask yourself, are these torques positive or negative? That is, are they clockwise or counterclockwise? So for example, this one causes clockwise or counterclockwise motion? Counterclockwise, right? So if I pull down, it causes this thing to rotate like this. So counterclockwise is positive, right? So I want you to find the torques, and then you add them up, and go and report the answer. I'll just step out and see our secretary. I'll be right back. Just 2 of you have clicked in? What shall we do with that? Calculating torque. Alright, it's still about 10 more seconds, 15 maybe. Say 2:35. That's almost everybody. 2, 5, 7, 11, 13, yeah. At 2:35. Okay, that must be right. Let's see, so. Did I tell y'all what I made on my last exam? I took it the other day. 100%. 100%. Like even better because there were a couple bonus questions, so I think I actually got like an extra 4 or 5 points. That's good, huh? Yeah. And I started out making C's in the class, but now I'm like the top student. I think. I don't know. Probably not the top student. Probably everybody's gonna make 100%. But I like to think that I'm doing well. All right. I'm working on an MDiv, a Master of Divinity. It's a class on the history of Christianity from the Reformation to present day. It's an interesting class. Okay. Let's see. So net torque. I have it rotating about axis C, about this axis. So this force is providing no torque at all because the moment arm is equal to 0. As you've already said, this torque is counterclockwise. So I'll call this torque 1, and it's going to be positive. This torque is clockwise, so it's negative. I'll call that torque 2. Now the way that you know this, I always like to use a pencil or whatever. And I can just hold it right there, and if I pull down in this direction like this force is doing, that causes clockwise motion. If I pull down in this direction, that causes counterclockwise motion. All right. And then so my net torque, the sum of all the torques, is going to be torque 1 minus torque 2, using that clockwise, counterclockwise notation for positive or negative. And then I just want to calculate torque 1, which is going to be 25 newtons, times r, which is 2 meters. That's the distance from where the force is applied to the axis of rotation, times the sine of 45, minus 20 newtons, times 2 meters. That's this distance, which is 2 meters, times the sine of 20. And is that equal, what was the answer? So that is equal to positive 22 Newton meters. And because it's positive, it's counterclockwise. This will become important because we'll start applying Newton's second law. And like we did before with Newton's second law, the sum of the forces equals ma. We'll have the sum of the forces will equal to what we call the moment of inertia times alpha. We'll be able to, if we find the sum of the torques, we'll be able to determine what is the acceleration of a rotating body. All right, let's try this one other one. It's like a seesaw, if you've ever been on a seesaw with a kid. Don't overthink this too much. If you didn't know, my name is Chad. My wife's name is Kaisa, so it's like it's me and her on the seesaw. Did y'all just get that? That's me and her. Yeah, really. I didn't have my beard when I drew that, so it does look a lot like me. It's just without the beard. So I might shave the beard off during the winter. I don't like having a beard during the winter months. It's not very comfortable. Well, I cycle a lot, and so like I wear something over my face. But when you have a beard, you try to wear something over your face. It's just not very comfortable. All right, let's stop at 2:20, 2:30. All right, good. So you ever seesawed with a kid? Right? What do you do when you seesaw with a kid? You have to get right. You have to get closer, right? So you can balance the torques out. Um, so if I have big ol' me and then a little bitty Kaiser down here at the end, that's never going to balance. You really want to switch it the opposite direction. So D is the right answer. Let's look at this problem. This is pretty simple. We'll see some that are more complicated on the exam, but let's just work through this. This is something similar. Let's say that I have a little girl and a little boy. These distances from the axis of rotation. It's pivoted at the center of mass right there. And let's see. Oh, the mass of the board here of the seesaw is equal to 10 kilograms. And the guy has a mass of 100 kilograms. The lady has a mass of 50 kilograms. And I want to know what is this length x for it to be balanced. Now I have three forces that are acting downward here. I have FW1 for the lady, FW2 for the guy. This is going to be 1,000 newtons. This is going to be 500 newtons. But then I also have the weight of the plank, and that's 100 newtons, because it's 10 kilograms times the acceleration due to gravity. However, what is the torque that's being provided by the weight of the plank? Right, there is no torque. So we won't even consider that when we're considering the sum of the torques. However, we do know that in this static situation, for this to be balanced, that the sum of the torques has to equal 0. We also know that for it to be static, that the sum of the forces has to be 0. So not only do the torques have to add up to 0, but the sum of the forces have to add up to 0. And those two guiding principles actually would be the principles when we go into next chapter on equilibrium. And those of you who are engineering, the 5 or 6 of you that are engineering, you'll spend a whole semester working on that. So have a whole semester of statics that you'll take when you go wherever it is that you go. We don't offer it here. Anyway, first let's look at the sum of the torques. There are only two forces that provide torques. There's this force and there's this force that provide torques. I can find the sum of the torques. Let's see, torque 1 here provides a counterclockwise rotation, so it's positive, and torque 2 provides a clockwise rotation, so it's negative. So the sum of the torques is torque 1 minus torque 2. That has to add up to 0. So that's going to be 500 newtons times 2 meters minus 1,000 newtons times x, and that has to equal 0. That's 1,000 minus 1,000 times x equals 0, so x has to equal 1 here. Okay, just over a little preview. Now we'll work on problems that are a lot more complicated than this for our equilibrium chapter, but same idea here is that the sum of the torques has to equal 0, and then also the sum of the forces has to equal 0. And if we know that the sum of the forces has to equal 0, then we can determine unknown forces, such as the normal force. So I have three forces, actually 4 forces that are at work on this. I have the normal force, I have FW1, FW of the plank, and FW2. And I know that the sum of those forces has to equal 0. So that's going to be Fn minus FW1 minus FW2 minus the weight of the plank, and that's all equal to 0. And then I solve for Fn. That's going to be, what were the weights again? 1,000 and 500, is that right? Yeah.
No, it was 150. The weights.
Oh,
You want the weights?
the weights, yeah.
The weights were 150.
You sure? Oh no, they were 500 and 1,000.
Oh no.
The masses were 150. Yeah. Yeah, so FW1 is actually 500 plus 1,000. That's 5,000. plus the weight of the plank, which is 100 newtons. It was 10 kilograms. So the normal force then is 1,600 newtons. All right. And again, that's a very, very simple equilibrium problem, statics problem. And next chapter we'll get into more complicated ones, more realistic ones. Well, that's realistic. It's just very simple. All right. We'll move on down from here. Okay. So let's look at kinetic energy. And out of this kinetic energy, we're going to define moment of inertia. And I'm going to show you several derivations for moments of inertia. And you could see that on the next exam, one of these derivations. I'll just expect you to memorize them, if you will, or think of the procedure. The procedures are all the same for finding these moments of inertia. So you can either memorize the individual ones or just try to remember the procedure for it. It's really the process that I want you to know how to do it. But first, let's look at kinetic energy of rotation. So we had kinetic energy for translational motion. So we can call this translational energy. That is the energy of an object moving in a straight line. However, if we have a rotating body, let's say that, I don't know, we have a hoop or whatever, or a wheel, it's rotating about this axis. We can take that and we can break it up into a bunch of little elements. What do we call these little elements? Well, it's written here, actually. We call these differential elements. Do y'all call them that? When you talk about differential elements at all in differential calculus? Calc 1? No? You don't really talk about it in that terms? Okay, well, when I have an object and I want to integrate over an object, or I want to, I haven't got to that yet. So when I have a derivative, right, that, like for example, we found the acceleration was dv dt, we break our time intervals into little bitty segments. Right, those are called differential elements. We make them very, very small, and we let that delta t go to 0. And when we let that delta t go to 0, get infinitesimally small, we call that a differential element. You never heard that term before? You heard it in Calc 3?
Just call them blocks.
Little blocks? Okay. Well, we call these differential elements, but you can call them little blocks if you want, and we're just going to add them up, okay? So each element has a different linear velocity. So if I have elements at larger radii, they're going to travel faster than objects at smaller radii, right? Because if you recall, our velocity is related to our angular velocity by the radius. So if the radius is big, everything's traveling at the same angular velocity. But if our radius is big, then that means that they're going to be traveling with a larger velocity. So if I have, say, a wheel, a solid wheel, I have a little block out here and a little block out here. These are both traveling with the same omega, but they're traveling with different velocities. So if I talk about the energy of each of these, one of them will have more energy than the other. So this one has the bigger velocity. This one has a small velocity in comparison. And so this one will have a bigger kinetic energy, and this one will have a smaller kinetic energy, because it's traveling at a slower rate. All right? So I can say then that since kinetic energy is 1/2 mv squared, since v equals omega r, I can get an expression for the kinetic energy in terms of omega instead of v, because v changes with radius, and we don't want that. We want something that's constant. So my kinetic energy then is going to be 1/2 m times omega r squared. All right, which is, I can rewrite this as 1/2 m r squared times omega squared. Now, as we said, omega is constant for a rotating body, for a rigid body. Remember, that was one of our qualifications for a rigid body, is that omega be constant. However, this quantity, mr squared, will change for the rotating body depending upon what radius you're at. So let's see, that was right there. So since the angular velocity is constant for each differential element, then we can find the total kinetic energy like this. It'll be 1/2 of the sum from I equal 1 to infinity of mr squared, mi ri squared times omega squared. So what I've done is I've taken this expression, mr squared, omega squared, and I'm making it more general. So I'm saying that now on my rotating body, say I have this wheel that's rotating in this direction, I'm adding up mr squared for each differential element, for each little block. You with me on this? All right, what's this the definition of, by the way? Anytime you think summation, you think what? Okay, a series, but it's a what? No. It's an integral, right? An integral is really just a sum. It's really just adding up stuff. So, so we're going to express this in terms of an integral. Now, for linear motion, we use the mass to describe the inertia. For angular motion, we're going to describe something called the moment of inertia. To describe the inertia of the rotating body. And the moment of inertia just describes how difficult it is to change the rotational motion of the object. Is that on the next page? Yeah. The rotational motion of the object. All right, we're going to define this based on that idea of kinetic energy. Go back to that. So see, we had this kinetic energy right here. Now, remember before, we had kinetic energy was 1/2 mv squared. But I've told you that now we're replacing v with omega. So where we had v squared before, we'll now have omega squared. So that's going to be omega squared. And where we had m before, we're now going to have this quantity mr squared. So our quantity mr squared is going to be what we call the moment of inertia. So we're defining what is the moment of inertia, and it's going to be this sum of mi ri squared from I equal 1 to I equal infinity. So we're breaking our object into an infinite number of blocks. So I can further say that di will equal to r squared dm. So it's basically taking this and making it into a differential expression like this. di is equal to r squared dm. Or if I integrate both sides of this, then I get a definition for I, which is just the integral of r squared dm. All right, so that's sort of a long way to get around to our moment of inertia definition, that it is the integral over a certain object. I'll show you how we'll do that next time, but it's the integral of r squared times dm. You with me on this so far? It'll make more sense when we get into it next time, I think. But also in the course of that, we also found this expression for the kinetic energy, which is going to be 1/2 I omega squared. And that'll come back a little bit later, and you have some homework problems that deal with kinetic energy as well of a rotating body. So whereas before the 1/2 mv squared was a rotational a translational energy, this is a rotational energy. So objects can have two types of kinetic energy. Just an object moving in a straight line has translational kinetic energy that's related to its mass and its velocity. An object that's rotating has a rotational kinetic energy. Might stop there. Let me see. Sorry, I lost my place. What page are we on?
47.
Okay, let's just finish this last little bit. So the units of moment of inertia are kilogram meter squared. We'll see that next time. And then the kinetic energy is going to be 1/2 I omega squared. Alright folks, next time we'll spend probably much of the class just finding moments of inertia for different shapes. And I said we just have a few more days till the exam. So be working on chapter 7 and 8 homework. Chapter 7 and 8. Yeah, just chapter 7 and 8. And that will be the next exam. Okay? Plus 70% will be from that material, and then another 30% from this statics, which I'll send y'all out some papers, and I'll print out some practice problems. We'll work some in class as well, okay? All right. That's all. Sorry to let y'all out early. I have this thing at teachers upstairs. All right. Y'all have a good weekend.